Okay, we're getting here into some of the details of how the nonlinear analysis might be done. The topics, we're going to look at static pushover analysis and dynamic step-by-step analysis, and displacement control, a few more aspects, la-di-da. These are the topics for this session. So let's look first at static pushover analysis and displacement control and the event-to-event method. We're talking here a static pushover. So the load sequence is to apply gravity loads first, and then keeping the gravity loads constant, add the pushover loads. You specify the pushover load pattern only, not the magnitude. You find the magnitude during the analysis. The gravity load is simple, usually linear. Sometimes if you use fiber cross-section, some of them can crack, even under gravity load, just a little bit, in which case you have to do a nonlinear gravity analysis, but it usually doesn't take very much longer than the linear one. The complicated part then is the pushover analysis. And the important thing here is it's done using displacement control, and let me explain what that is if you don't know. This illustrates load control versus displacement control. Load control first, what you do is you apply a number of load increments, typically uniform but not necessary. And what you'll get is as you apply uniform load increments and the structure gets softer, the displacement increments will get progressively larger. And one thing that happens, if you try to apply a load which is larger than the strength of the structure, well, there is no solution, and the analysis will simply not be able to find a solution that will stop. So this is not a very good method of doing static pushover. A much better method is to use displacement control, where now you start by applying equal displacement increments, and you calculate what load increments you require to do this. And those load increments can be negative, and so you can trace out the behavior beyond the point where the maximum strength is reached. I do want to emphasize that displacement control, the last point here, displacement control is not the same as imposed displacements. If you did impose displacements, you would grab the structure and you would impose a particular displaced shape on the structure. That's not what we're doing. We're applying a load to the structure and letting it displace in the pattern it wants to displace based on that load. But we're just going to determine how much load does it take to push the structure over a certain amount, and then how much more load to push it over another certain amount. It's actually easier than imposed displacements. And it's very simple. The way it's done is this. Step one, you start here at the beginning of the step. Step two, you have the specified displacement increment that you want for the step. Step three, you just choose any arbitrary load increment. It doesn't matter what it is, and you apply that load increment, and you do a linear analysis, and you calculate this much displacement increment. You say, well, that's, in this case, more than I want. I'm just going to scale a load increment back to this point, and then this is the load increment that was required to produce this displacement increment. So you apply an arbitrary load increment, and you just do one relatively, usually pretty simple operation to scale it back to get the displacement you want. And the sort of thing that can happen if you apply a load increment and it decides it wants to move back in the other direction, well, that just means you have to apply a negative load increment. Thank you very much, sir. You have to apply a negative load increment. It's not quite that simple because you're into things like negative stiffnesses, but it can be made to be very reliable. So a displacement control procedure is really basically simple. Now, event-to-event is something different. If you have linear analysis, it just moves backwards and forwards along this line. So you have a constant stiffness, the loading, unloading parts are pretty simple, and the analysis is basically a pretty simple process. When you have nonlinear behavior, here I've shown a number of linear segments. It's straight, and then the stiffness changes. Here's an event, another event, and so on. So the stiffness progressively changes. You can have complex loading, unloading paths. This one comes up to here and unloads, but if it goes up somewhere else and unloads, it'll come back along a different path. So it's a lot more complex than linear analysis, and it's just not so simple. The key points are that a significant stiffness change is a nonlinear event. And in this particular case, we have yielding events and an unloading event. So the most common events are yielding, where the stiffness reduces, and unloading, where the stiffness increases. But there are many other things which can lead to changes in stiffness. And what Perform uses is the event-to-event strategy, where it basically just goes from event to event and calculates when the next event is going to occur, and then modifies the stiffness to take account of the event. It's really kind of simulates fairly closely what happens in reality. In reality, the thing does go from event to event, but there are an infinite number of events because it's a continuously changing stiffness. The model is a finite number of events. There are many other analysis methods which don't go event to event. They tend to be iterative methods of Newton type, and they can be more efficient, but they're also generally a lot less reliable. So if you have displacement control and event to event, this is the sort of thing which is happening, is you have some specified displacement increment, and it's not shown here, but you would first of all apply some arbitrary load increment. This would come out here, and you would scale back to the event, to the displacement you want, based on linear behavior. So first of all, you arrive here at point 2. Then you say, oops, we had an event occur here before we got to this point. So you have a second scaling, which brings you back to the event. Then you reform the stiffness, and you continue. And if necessary, if there's another event occurs in here, well, you just repeat the process all over again. So it's a displacement control with event to event. You can also use event to event with load control. And here it is with event to event with load control. You apply the specified load increment, linear solution, scale to the event, another linear solution with a different stiffness, scale to the event, another linear solution until you finish up applying the entire load. If we look at reliability and efficiency, I think that the event-to-event is the most flexible and reliable method. That's the reason I chose to use it in Perform. It's the only method which is available. You can use it for displacement control or load-controlled analysis, and also for static and dynamic analysis. It has a major disadvantage, that the stiffness must be modified at each event. And I must let me say that one way to modify the stiffness is to reform it completely. That is really rather expensive. Another way is just to recognize there are just certain limited changes in the stiffness matrix, so just do a modification rather than a complete reformulation. That is a lot more efficient. The disadvantage, though, is as the structure size increases, a couple of things happen. The number of events tends to increase. It's just a bigger structure. There's more events that can occur. And at each event, you have to modify the stiffness, so the computer time to modify the stiffness increases for each event. So you have more events, more time to modify the stiffness for each event, and the computation cost tends to increase exponentially as the structure gets larger. Nevertheless, although there are a number of other strategies, and sometimes they can be faster, my experience has been is that they're more difficult to use and less reliable. And I think even given the disadvantages of the event-to-event method, it still is the best method. And Perform 3D, I think, has proven to be very reliable, and it is competitive in speed. I'll show later on, if you've got some monster structure, it can take a long time to analyze, you have to admit that. But most structures which are reasonable size don't take an outrageous amount of time. And as computers get faster and faster, we'd hope that the analysis times will get less and less. So the next topic, that was just very briefly on the basic method. A few more advanced aspects. This is something that you do need to consider, and this is controlled displacements. And as I showed, in a displacement-controlled analysis, you increase the displacement in equal increments. And the thing is, the structure has got lots of different displacements, thousands of different displacements. So which one do you want to increment? You can choose any one of those 1,000. Now, what you do in Perform, and let's look here at a pushover analysis. There are two key displacements. Firstly, there's a reference displacement, and secondly, there are one or two controlled displacements. I'll illustrate this graphically, by the way, in just a moment. The reference displacement is usually the displacement at the roof. And when you plot a pushover curve, it's basically base shear versus roof displacement. Sorry, base shear versus roof displacement. And so that is the reference displacement, and it usually is the displacement at the roof. But there's a second type of displacement, and this is the one that you want to increment equally in each step. Now, the obvious choice, and the choice you frequently use, is the same displacement, the roof displacement. But it doesn't have to be. If you use only one control displacement, this will be the roof displacement. And this is then incremented in equal steps. But what may happen is the roof displacement may not be well behaved. And without going into more detail on that, let me just illustrate this in the next example. Now, we'll spend a little time on this, but here's a two-story structure. And we have a displacement at the first floor and a displacement at the second floor at the roof. And let's suppose that the upper story has behavior like this, which is linear. So loads of 5 and 10 for H, and some displacements and a stiffness of 5, which gives you displacements of 1 and 2 for loads of 5 and 10. And this then is the displacement delta 2 minus delta 1, so the story-to-story drift versus the story shear. And the lower story, let's say that one is nonlinear, and it has an initial stiffness of 5, and then it yields, then it suddenly loses strength, and so on. So if you look at the behavior of this, when you combine these two together, let's have a look at what is happening, is you go up to a load of 10, the displacement in the upper story is 2, the displacement in the lower story is 2, so the total is 4. Then this one yields, so the load stays at 10, and the displacement in the upper story is still 2, displacement in the lower story is 4, so 4 and 2 is 6, so you've come out here and the displacement is 6. Then this one suddenly loses strength, so now the load is 5 and the displacement is 4, the load up here is 5 and the displacement is 1, 4 and 1 is 5, so the displacement comes back to 5, and then it continues horizontally. So the roof displacement has doubled back on itself. This is bad. Now, this is a badly behaved displacement. And if you want to if you say, okay, I want an analysis where I increase this displacement in equal steps, you're going to run into real trouble here because it doesn't want to increase, it wants to decrease. So what do? Well, it's very, very simple. You say, okay, I will specify that I want delta 1 or delta 2 to increase, whichever kind of comes first. And I specify 2 control displacements rather than 1. And if you have a large and complicated structure, it's probably not a bad idea to even have a control displacement for being the drift at every story. It can often be a pretty good idea. And so now what Perform does is says, okay, I'll just move along, but at each step, it'll look for a well-behaved displacement, a displacement which it can increment. So for the first few steps, it may choose, in this case, the roof displacement. When the roof displacement starts to behave badly, it's able to detect this, and it'll switch and it'll increment the next displacement down. And it'll continue on. You won't get nice equal displacements at the roof, but you'll still get a good curve. So this particular example illustrates a badly behaved displacement. It also illustrates that particularly if you have strength loss, in fact, always if you have strength loss, you must use multiple control displacements because otherwise you can get into trouble. Another thing which is done is event overshoot. I'm not going to spend much time on this because this is a little bit complicated, but if we had a low displacement curve that looked like this one here, then we have an event, an event, an event, an event, event. So there are several events along this. And if we went exactly to the event, we'd go from here to here, reform the stiffness, here to here, reform the stiffness, here to here, et cetera. And there'd be several stiffness reformulations. But suppose you said, well, I'm going to define the event as being here, where I allow a certain amount of overshoot between the exact event and what I'm going to call the event. So I'm going to go to this point, and this will pick up, in this case, 3 events. Right? So a single event which encompasses 3 rather than 3 separate events. So you've saved some time. The price you've paid for this is you have an equilibrium error because the structure is really here, but you've applied this much load, so you have to apply a correction. Typically in Perform, the overshoot tolerance is small, 1% of the component strength, and so you hardly see it. But you have an option in Perform to increase the overshoot tolerance to as much as 20% of the component strength. And usually if you have a complicated structure, I usually recommend you do that, because if it's a complicated structure, it's got more ways in which you can sort of redistribute the load. And you can usually get away with a larger overshoot tolerance and save yourself a significant amount of computation time. This applies both to static pushover and to dynamic analysis. I'm not going to spend any time on this one. You can take a look at this separately if you want to, but the price you pay for allowing overshoot is you get some equilibrium unbalance. You have to correct for this, otherwise you get the wrong result. And all this diagram does is just indicate how you can correct for the equilibrium unbalance. And it's done in the next event, basically. So what you do have to specify certain things in Perform 3D when you do a static pushover analysis. You don't have to know a lot about the analysis method, but you still have to specify a few things. Firstly, you have to specify the pushover load pattern, and you have a number of choices. You can use a specified load pattern. You can specify a displaced shape, and it will calculate the forces based on that displaced shape and the masses. For example, if you specify a linear displaced shape over the height of the building, this would correspond to a triangular load pattern, but based on the masses. You know, the loads don't necessarily increase linearly. The load at any floor is the mass at that floor multiplied by the height up to that floor, which is really what you mean by a triangular load pattern rather than one which is truly triangular. So you must specify that. And the third choice is you can specify loads which are based on the masses and the mode shapes. It will calculate mode shapes, then construct lateral force patterns which are based on the masses and those mode shapes. So they're modal loads. Secondly, you must specify the maximum displacement, or in Perform, it's always a drift ratio rather than a displacement. And we ask you specify a reasonable value. 20% drift is huge. You know, there's not really any point in pushing over something to 20% drift. Why waste computer time? Yeah, 5%, maybe 10% is more than you're ever going to need. So specify a reasonably realistic value. Thirdly, the number of equal displacement steps that you want. And I suggest maybe 50 as being a pretty good number. I do see people using 500, but that's really overkill. And in fact, it creates problems because if you have a very large number of very small steps, the displacement displacement control method can get a little unhappy because you get so little load increment it can get sort of messed up. It's better actually to specify 50 or maybe 100 steps, but no more. You don't need to do any more than that. You then specify the maximum number of events in any step. Sometimes the analysis can go wrong. It doesn't happen very often. And then it'll just get into some loop and it'll just get event after event after event. Unless you do something to stop it, it'll just run forever. So we ask you to specify the maximum number of events, and it depends on the size of the structure. If it's a small structure, maybe 50. If it's a big structure, well, specify 1,000. If it gets unhappy, at least it's going to stop sooner or later. And if it exceeds that number of events, it'll just quit, says something's gone wrong. Then a limit state to stop the analysis if the deformations become unreasonably large. The structure can start to collapse or something like that, and you get some very large deformations. There's no reason to continue the analysis beyond that point because something has gone wrong. Either your model is wrong or something like that. What you usually do, if you recall the force deformation relationship in Perform is this YULRX, and X is a large displacement beyond which there really isn't much point in continuing the analysis. The default for this limit state in Perform is that if any element or any component reaches its X point, then the analysis will stop. It's saying there's really no point in continuing. So what we usually recommend you use this default and specify at the component level, reasonable X point deformation, not huge. You don't have to specify 10% strain or 100% strain or something like that. Some reasonably fairly large value so that you can know if it gets that far out, there's really no point in continuing the analysis. And then it'll stop. And finally, the amount of event overshoot, and the default is 1%. And as I said before, you can often increase this number for large structures, and you can go as high as 20%. So next stop, we're still on static pushover analysis. Next event, how is it used? And we used this slide before. Step 1, you choose the loads. Step 2, you get the pushover curve. And then step 3, using a response spectrum, you estimate the target displacement. And step 4, you calculate limit state usage ratios at that target displacement. So there's two things. The pushover analysis just gives you a pushover curve and nothing else. The key thing is for performance evaluation, you have to get the performance point or target displacement. And I did show a Perform 3D example where it did that. I didn't earlier on in session 1. I didn't explain how that was done. Here's one of the methods, and this is the coefficient method, which is the method that is in ASCE 41. Let's run through this thing step by step. We calculate the pushover curve, shown here dashed, and step 1A is to estimate the target displacement delta. Just guess something. Then, using that, construct a bilinear approximation. One of the things I did in the example was choose a number of trial points and construct a bilinear approximation for each of those trial points. When you do that, you have now a stiffness, and using that stiffness, you can get a period. I'm not going to go into the details, but if you know the stiffness, you can do that. So you now have a period. You come over here with that period, and you go into the response spectrum, and you come out with a spectral acceleration demand. You bring that spectral acceleration demand over here, and you can convert that to an equivalent horizontal load. Say simple lollipop is very simple. If it's a more complicated structure, it's theoretically a little bit complicated, but you can do that. And you then come across here until you meet this linear curve. Now, this is basically, if the structure remained linear, this is the displacement that you would get. If the structure remained linear with this stiffness, which is not necessarily the same stiffness as the initial stiffness of the curve, it may be smaller than that. Then you do using some empirical formulas, you calculate some factors C1, C2, and C3, and you scale this to get a better estimate of the displacement. If the product C1, C2, C3 is equal to 1, and it often is, then it's going to be this point, and this is then exactly the same as the old constant equal displacement assumption that says that if you run a linear analysis and a nonlinear analysis, the displacements will be the same in both cases. That kind of is the same thing. Usually, though, these things will be somewhat larger than 1. So now you have this point here. So you started off with a guess, and then you calculated this. If these 2 points are the same, or the two deflections are the same, you've converged. If not, you have to try again. What Perform does is for each of the trial displacements, it calculates this point, and it plots those points as a curve, and where they cross, that's the performance point, which is what we did in session 1. Now that's one method, and there are a couple of variations on the coefficient method with different ways to calculate C1, C2, and C3. There is also what is known as the FEMA 440 linearization method, which is a new method. And then there's an older method, which is the capacity spectrum method, which has a number of variations. So there are several different methods of doing of estimating the target displacement from a pushover curve. And I'm not going to do any more of them here, but in the notes there is a copy of a paper that explains in some detail the steps for each of the different methods. It would be very nice if they all gave the same results. Unfortunately, they don't. They can give sometimes substantially different results, and this is just one of those issues which needs to be resolved. Here's what happens in Perform 3D, and we've seen this sort of thing before. You get a number of trial curves, use your demand curve, and the capacity curve. So the next topic is what are the advantages and disadvantages of static pushover analysis? Advantages, it uses a response spectrum, whereas dynamic analysis requires ground motions. That, from a design point of view, is a major advantage. It requires less computer time than dynamic analysis, possibly a lot less computer time. And it can provide some sensitivity information on the effects of changing strength and stiffness. I don't know if you recall, but there was a demonstration in session 1 which indicated you get some idea of what would happen if you were to increase the strength and stiffness, or what would happen if you just increase the strength, keeping the stiffness the same. So it does have the advantage, it can give you some sensitivity information. The disadvantages, firstly, it does not account directly for the dynamic nature of earthquake loads. It uses static analysis to approximate dynamic effects. It does not account directly for hysteresis loops. So if you have stiffness degradation, energy dissipation, etc., that's not considered in the pushover curve. It has to be considered indirectly. And this can complicate the thing. It means it becomes rather an empirical method where people just run lots and lots of earthquakes past structures with lots and lots of, with a number of different hysteresis loop shapes, and massage the results and come up with some empirical formulas. And I don't like that sort of method personally very much. I've never liked empirical methods. But the only sort of non-empirical method is the old capacity spectrum method that tends to sort of at least give the semblance of being a little more rational. Unfortunately, it's a very nice method conceptually, but it doesn't work very well in practice. And so, unfortunately, it's not a good method. Static pushover analysis is a valuable part of the design process, but as a method for performance assessment, it does have limitations. Let's move on to dynamic step-by-step analysis and start off with advantages and disadvantages. Disadvantages: the dynamic analysis model is rather more complex than the static pushover model. Not a lot, but some. You can't use a response spectrum, you require ground motions. The response can be sensitive to changes in the ground motion, sometimes rather remarkably sensitive, unfortunately. So you have to carry out analyses generally for a number of earthquakes, and 7 is a common number, so it can get to be a lot of analyses. Each analysis requires more computer time than pushover analysis, and it doesn't give sensitivity information, so it's kind of rather more difficult to evaluate alternative designs or decide what to do if something doesn't work. And we've been through this before. If you use capacity design, it's a lot easier to decide what to do. If you haven't used capacity design, it's a lot more difficult. The advantages is that it applies to structures of all types. It accounts directly for the dynamic nature of earthquake loads, which can be important. It accounts directly for hysteresis loops and energy dissipation, or it should. You know, if you run a dynamic analysis and there are degrading loops, your model should reflect that. So it's more general and it's more accurate than pushover analysis. And as computers get faster, and if they ever work out this issue of how to choose the ground motions, I think you can expect over time that dynamic analysis will be the standard and pushover analysis will be something you'll look at but not use for the final determination of performance. Dynamic step-by-step analysis, is it feasible, and how much computer time does it take? I'm just going to give some examples here. Here's one example. It's an 11-story steel frame, 3 by 7 bays. It's got 720 nodes, 2100 degrees of freedom. The model has got 960 inelastic beam and column elements, 320 inelastic panel zone elements, and it runs 1,000 steps, a 20-second earthquake with 1,000 steps on a decent 3 gigahertz PC. And it depends a bit on the intensity of the earthquake, but of the order of 10 minutes for one earthquake. If the earthquake's not too strong, 5 minutes. If it's real strong, it might take 15. It's of this order of magnitude, and that's not unreasonable. This is rather more complicated, 61 stories, shear wall building, 2250 nodes, 1600 degrees of freedom. This is a small structure by linear analysis standards, but for nonlinear analysis, these are getting to be pretty major structures. 1,200 elastic wall elements and 120 inelastic wall elements. Now, the person who modeled it just used inelastic wall elements rather selectively and assumed the rest of the structure was elastic, which reduces the computation time quite substantially. It's got 320 beams and columns. It's got some outriggers with some buckling restrained braces, so it's got some of those. And again, a 20-second earthquake. This takes 1, 2, maybe 3 hours of computer time depending on the intensity of the earthquake. Again, not unreasonable. This one was the granddaddy this isn't a Guinness World Book of Records standard, but it's getting pretty close, I think. This was actually the very first one we did with Perform 3D. This is a plan view it's a shear wall building, and every one of those lines is a shear wall, and it's 50 stories tall, so this is really quite a monster. There are coupled shear walls with openings all over the place. Got 50 stories, got 17,000 nodes, 48,000 degrees of freedom, 12,500 inelastic wall elements, la-di-da-di-da. It takes about 3 days for one earthquake. You know, for a more realistic structure, an hour is a more realistic thing. If you want to do a really king-size structure of this magnitude, you've got to expect it's going to take a while. And this, of course, is a PC, and this is only a 2 gigahertz PC that was done a number of years ago. So one of the things I said before is as a structure gets bigger, the time does tend to go up exponentially, but you can run very, very large, very, very complex structures in times that are not unreasonable if you have a certain amount of patience. Hysteresis loops. Now, if you're doing a nonlinear dynamic analysis, you will need to model hysteresis loops. And there's a number of possible shapes. You know, the first one shows cyclic strength loss. Next one, cyclic strengthening. There's what is commonly referred to as in-cycle strength loss, where you lose strength and then does something after that. You can have pinch loops, a buckling type loop. A fluid damper has got something which tends to be almost square. There's a variety of different hysteresis loop shapes. These are the main issues. Under cyclic loading, the inelastic components dissipate energy, and the dissipated energy is simply the area under the hysteresis loop, or the sum of the areas under all of the loops. And the sizes and the shapes of the loops can significantly affect the response of the structure. The conventional wisdom says if you get into rather long period structures, that the amount of damping shouldn't have very much effect on the result. But that doesn't always seem to be the case. This is a little tricky one. If there is degradation, then I think you should attempt to model it. And within Perform 3D, you can do that. We'll talk about that in a moment. In static pushover analysis, you don't consider hysteresis loops. They're considered only implicitly. But in dynamic analysis, they can be and must be considered explicitly. And different components can have different hysteresis loops. These are the major issues. What ASCE 41 says is the following: the complete hysteretic behavior, each component should be modeled la-di-da. And the use of the FD relationship shown below shall be permitted. And unloading and reloading shall represent significant strength and stiffness strength degradation character. You can read better than I can. ASCE 41 is saying that you can use this curve as the bounding curve or the backbone curve, which I'll explain again in just a moment, but there's certain other things that you should do if you're going to do a dynamic analysis. And it doesn't give any guidance on this. You have to use your judgment and or available experimental results. The way it works in Perform is you have a basic hysteresis loop. And let's look at the diagram first. Here's kind of the way it might work. The YULRX would be the backbone curve. And without going into too much detail, this backbone curve kind of defines the shape of the hysteresis loop and sort of bounds the hysteresis loop in a way. But this defines the shape of the hysteresis loop. If you have cyclic strength loss, or if you cycle to the same amplitude of deformation several times and you get degradation, Perform does not consider this, and I don't think any others do. This was something I discussed briefly in the first session, that in the long term you can expect that you will model this sort of effect directly by having a monotonic curve and a fully degraded curve, and it'll change progressively from one to the other. Right now, the backbone curve that you have should represent a reasonable amount of cycling. And the backbone curves that are given in FEMA in ASCE 41 do represent a certain amount of cycling. So the last point, the loop does not account for progressive strength loss under constant amplitude cycling. This must be accounted for in the backbone relationship, and this is rather important at the present time. Now, Perform gives you a fair amount of control over some of the details of the loop. Firstly, you can control the amount of energy degradation. And without going into too many details, what you can do is specify degradation factors. And if this is force and deformation, and this would be the force and deformation relationship, what you can say is as the maximum deformation increases, the area of the degraded loop compared with the area of the non-degraded loop varies. And if before yield and shortly after yield, there's no significant energy degradation. If we cycle backwards and forwards at this level, so cycle backwards and forwards here, you'd say that the area of the degraded loop is about 90% of the non-degraded area. This is the non-degraded loop is dashed, the degraded loop would be here. If you go out to the L point, maybe 0.7, here 0.4, here 0.3, you get to pick your own numbers. I was talking to somebody earlier about the coupling beams in the example structure we looked at in the last session, and what was used for those coupling beams was a factor of 0.15 for basically all displacements. So there was assuming a lot of degradation, that the area of the degraded loop under cyclic loading was only 15% of the area of the non-degraded loop. But you can specify any numbers you like if you have experimental data available. It's not too difficult to pick some reasonable numbers. That's the first thing you can do, is you can control the amount of energy degradation using degradation factors. Secondly, you can control the unloading stiffness. And what we have here is 3 loops, A, B, and C, all with the same amount of energy degradation, about 50%, I think, roughly in this diagram. What's happening here is, again, the dashed is the non-degraded loop, and this is just a bilinear behavior. Here what you do is you have the maximum unloading stiffness, but the minimum unloading range to produce this degraded loop. Here you have the opposite. You've got the maximum unloading range, which would give you the minimum unloading stiffness. And here you have something halfway between, an unloading stiffness in between the maximum and the minimum, and an unloading range somewhere between the 0 and the maximum. And if you have an idea of what the shape of the curve is, there is a factor in there that you can specify which enables you to control whether it's of loop A or loop B, which are the 2 extremes, or somewhere in between. There's a factor you can specify to do that. It's the second thing that you can do to control the shape of the hysteresis loop. The third one is called strength loss interaction. Again, this is the backbone curve. If you deform it out to here and then have a hysteresis loop, if there's no strength loss interaction, the strength in the opposite direction will not be reduced. If there is strength loss interaction, the strength in the opposite direction will be reduced. And it depends on what type of structure it is. Some cases there is strength loss interaction, in other cases there's not. And one of the parameters you can specify and perform is a strength loss interaction parameter. And I think if you specify 0, it assumes this. If you specify 1, you get the same amount of strength loss in the opposite direction as you got in this direction, and somewhere in between is proportional. So if you have some idea of what the effect of strength loss is on the hysteresis loop, you can take this into account also. Those are the 3 things you can do with the basic loop, and almost all the components in Perform do have the same force deformation relationship and similar hysteresis loops, the similar ways of controlling the loop. It is an advantage, I think, of Perform that all the components have sort of the same look and feel. You don't have to learn 50 different hysteresis loops. You just need to learn one, and it does give you a fair amount of control over the loop shape. There are some special cases. I mentioned these before. If you have a buckling restrained brace, it can harden isotropically. If you have buckling, it has a special loop. And if you have concrete, this also has a different loop also. There is no provision for pinched shapes directly. However, what this is a plot of a hysteresis loop obtained by doing a cyclic pushover on a wall with a fiber cross-section. And the fiber cross-section automatically will give you a pinched hysteresis loop. And so this comes out of the analysis. It's not something which is specified directly. Let's look at damping. And this damping in dynamic analysis is a tough issue. Firstly, let's look at the purpose. And let's look at an elastic structure dissipates energy. An elastic structure doesn't lose energy. It's elastic. Any energy you put into it is stored as strain energy. It can come back out again. So if it's an undamped structure, which is going to vibrate, but if it's damped, we know from experience that energy will be lost. It'll be dissipated in some way. And it'll be dissipated in a variety of mechanisms. It could be somewhat inelastic behavior. It could be rubbing of partitions. It can radiate energy into the soil. There's a bunch of different things can happen. They're rather difficult to identify exactly what these mechanisms are, but this is almost always modeled as viscous damping for analysis. It's not viscous damping. It's highly unlikely that it is. So viscous damping for linear analysis is a modeling assumption. Typically, 5% viscous damping is a common assumption. And that's been established as being a reasonable assumption to make in most cases. Okay, now when a structure yields, it actually dissipates energy more directly, and this is through inelastic action. You go around a hysteresis loop inelastically, energy is dissipated by inelastic hysteresis. So you are directly modeling some energy loss. And the dissipated energy for a component is the area under its hysteresis loop or loops. What you'll find, you might say, okay, well, if we've got energy dissipation through inelastic behavior, we don't need viscous damping. Well, unfortunately, that's not true, because experience shows that if you ignore viscous damping and consider only the inelastic behavior, this does not account for all of the energy losses. There are more energy losses in the structure than can be accounted for by the inelastic components. So you still need some other means of dissipating some additional energy. There's still a lot of this elastic, quote-unquote, energy dissipation, and this is almost always modeled again as viscous damping. But we do have to be a little more careful. So for nonlinear analysis, you have no mode shapes. So you can't just say, well, 5% modal damping. You can't really use that. And I do have a qualification here is, as the structure deforms and the stiffness changes and hinges form and things like that, effectively the mode shapes change. And instantaneously you could say, well, there are some mode shapes, and maybe theoretically every time there's a change in stiffness you could recalculate the mode shapes and then you could use modal damping. But that's a hideous amount of computation if you had to recalculate the mode shapes at every event. I mean, it's absolutely prohibitive, so you simply can't do that. It's not necessarily a good idea anyway, quite apart from that. So we can't use the old 5% modal damping. We have to use something else. And Performer's got two models. One is Rayleigh damping, and the other is modal, quote-unquote, damping. Let's look at the damping matrix and the damping forces just initially. We're looking at equilibrium as this first equation. You have some external force must equal some internal force. This is dynamic equilibrium. And the internal forces are those associated with the stiffness of the structure, the mass of the structure, and the damping. And it's this damping forces we're going to be interested in here. For linear analysis, the stiffness force is simply the stiffness times the displacement. For nonlinear analysis, the stiffness is changing all over the place, and basically it's kind of the sum of a tangent stiffness times some displacement increments. For both linear and nonlinear analysis, the inertia forces are mass times acceleration. Those are the same, and that's pretty easy to calculate. And the damping forces are damping matrix times velocity, or C times r dot. M and K are well defined. The big issue here is we need to get damping forces, so we need a damping matrix C. And how are we going to do that? Well, Rayleigh damping postulates this, and it has a physical meaning. And the diagram up here sort of illustrates this. This is a simple frame with a column with a stiffness Kc, a beam with a stiffness KB and another column with a stiffness KC, what Rayleigh damping says is we'll put in parallel with the column a damper with a damping matrix beta times Kc. It's the beta K damping. What this says is the damping matrix of that column has got exactly the same form as the stiffness matrix, but it's a damping matrix, and the units get changed because it's a damping matrix. And the same for the beam and the same for the other column. And in addition, it's a stiffness-dependent portion. In addition, there's a mass-dependent portion that says that every mass has attached to it a damper with a value alpha times that mass, and that's connected to the ground. This is all the ground. So it exerts forces on the structure. So the damping matrix is alpha times the mass matrix plus beta times the damping matrix. What happens is the alpha M dampers exert external damping forces on the structure, and the beta K dampers exert just internal damping forces, sort of in parallel with the elastic forces. And incidentally, in a linear analysis, modal damping also exerts both external and internal forces on the structure. You don't see what they are, it's kind of hidden, but they're there. So this has a pretty clear physical meaning. Whether it's good or not is a separate issue, but the physical meaning is fairly clear. The thing, if you're going to use this model, how do you calculate alpha and beta? It's not so clear how to do that. If we look at what Rayleigh damping means in linear analysis, and not linear now, without going into too many details, what you can show is if you look at the damping ratio versus the structure period, that Rayleigh damping means that the damping ratio varies with period with a curve like this. It has two components. One component, the beta K component, as the period increases, the damping ratio gets smaller. The alpha M component, as the period increases, the damping ratio gets larger, and you get the combination. And between a couple of periods, TA and TB, you can get pretty much constant damping. And the one thing you can do is if you use TB as 0.9 times the first mode period and TA as 0.2 times the first mode period, you can then calculate the required alpha and beta to give you this curve. And over a range from about 1/10 of the first mode period to 1.0 times the first mode period, you've got pretty much constant damping. Beyond the first mode period, it doesn't matter because it's the longest period. For shorter periods, you get progressively heavier damping because of the beta K effect, which often the response from the higher modes isn't very significant, so the fact you damp them out may not matter too much. But it's not the same damping ratio in every mode. You're getting higher damping ratios in the higher modes. So in Perform 3D, this is a suggested procedure, and this procedure seems to work the best, is you pick the damping ratio. It doesn't have to be 5%, but it is typically. Calculate the first mode period. Well, Perform will do that for you. And specify a couple of values, typically 0.2 and 0.9 times the first mode period, and tell Perform that this is what you want. And it will calculate the alpha and beta values that are required to do that. You don't have to calculate them yourself. And it seems to work fairly well. Yeah, we have time. And there's an interesting contradiction here. This graph I showed before is damping ratio versus period, which says that as the period gets larger, the damping ratio gets higher. What happens in a nonlinear structure is that it tends to yield, and there's a tendency for the periods to increase. If you look at this would suggest that as the periods tend to increase, then the amount of Rayleigh damping should get larger because of the increased period. However, that's not correct. The reasoning is, I used to think that too, but the reasoning is false, and there's roughly a reason. So as a structure yield, as periods tend to increase, we might expect the viscous energy dissipation to increase. But let's look at this. Take a given amplitude of vibration, and suppose that the period is increased. So it's vibrating over a given amplitude, and it yields, and so the period increases. So the period increases. This means that a longer period means smaller deformation rates, but the damping matrix C is a fixed quantity. If you have smaller deformation rates, this means you have smaller damping forces as the period increases. This means you've got less energy dissipation as the period increases, you get less energy dissipation. And the point I want to make here is that if you look at this curve, you think, oh yeah, as the period increases, I'm going to get more energy dissipation. In fact, the opposite is true, you get less. And it's just something to think about. If we look at modal damping for linear analysis, in a linear analysis, the modes are all uncoupled. That means that the structure vibrates independently in each of the modes, and they all get mixed up in some way. And modal damping corresponds to a specific damping matrix, and I'm not going to get into details, but this is what it means. If you look at what the damping matrix is for a linear analysis, it's the sum over all the modes of the damping ratio term and the period and the mass matrix and the mode shape and a few things like that. So you don't ever evaluate it explicitly, but it does mean a specific damping matrix. What you can do and perform is you can say, okay, let's use that same damping matrix that you would use if it was linear. And that you can use the same damping matrix based on the mode shapes and periods for the initial elastic structure. And this damping matrix stays constant. And then if you wish, you can use that damping matrix. And you can specify, maybe calculate 20 modes and then use 5% damping over those modes using this damping matrix. And it seems to work okay. But there are some things that happen. What is the effect of the modal damping on the stiffness matrix? Well, the mass matrix M is diagonal. The stiffness matrix K is banded. If you don't understand this, don't worry. This is just a computational detail. And then the Rayleigh damping matrix is a combination of M and K, so this is also banded. But the modal damping matrix is a full matrix. That's just the way it happens. And in order to solve a set of equations efficiently, you need to take account of damping and of banding. And if you have a non-banded stiffness matrix, the amount of time to solve the equations can go dramatically higher. So what perform does is say, well, okay, the portion of the damping matrix which is inside the band, we will do that properly, and we'll handle it during the equation solving process. But this portion outside the band we'll handle by what is called a right-hand siding process. We'll delay applying it and apply it in the next step. And it produces some temporary unbalances, but in many cases seems to work okay. So you can do this. If you do that, you're not damping every degree of freedom in the structure. You are damping a certain number of modes. And what this one says is that suppose you have a structure with n total degrees of freedom, say 10,000, and you damp out, say, 20 modes. Well, that means there are 9,980 degrees of freedom that it can have which are completely undamped. It's not a good idea to have undamped degrees of freedom floating around. They can create problems for you numerically. So what we recommend is you add a very small amount of Rayleigh beta K damping to damp out the high-frequency vibrations, just a very small amount. And this also seems to work well. It doesn't add anything significant to the total energy dissipation, but it does stabilize the solution process. One of the things you need to do is that this is taken from Perform, which is an energy balance. And this particular one here actually is dissipated inelastic energy. This actually comes from viscous dampers. And this is from, I think, alpha M damping. And then you got the light blue is strain energy and the dark blue is kinetic energy, but this is an energy balance. And one of the things you should do is kind of take a look at this. And here's one example of an energy balance. The first one here is with Rayleigh damping, and this is beta K damping energy, and this is alpha M. And the second one is with modal damping, and the red here is inelastic, and this color here is modal energy dissipation. And if we look at the values, this is a 3-story frame building. It's just a little example I used earlier. The left figure has got 5% Rayleigh damping at the 0.2 and 0.9 T1 as we suggest. The total energy dissipated and calculated is 558.80. Inelastic is 3030, and the roof drift was 2.97% from a dynamic analysis. When we do the same thing with 5% modal, very, very close total energy, very, very close inelastic energy, very, very close displacements. No significant difference for this frame for this particular case. It looks like both methods work particularly well. Of course, it's never quite as good as that. This is a different example, which is a 10-story concrete shear wall. And again, this is Rayleigh, and this is Modal. And notice much more energy dissipation proportionally from Modal. But anyway, total energy 4762 versus 4460, not too much difference. Inelastic energy 1024 versus 800, substantially bigger difference. And the roof drift, well, again, not too much difference. But we're starting to look at some significant differences between the two models. And they're different models, this is to be expected. And I might say that we found that the two methods seem to agree pretty well for frame structures, but they may not agree quite so well for shear wall structures. And what I've been suggesting people do is to use the Rayleigh damping for shear wall structures rather than modal damping. It seems to work rather better. That's just one of those things which we have to do some more work on. Finally, step-by-step integration through time. If we look at a single degree freedom system, basically you've got the ground acceleration, which is exciting the structure. This produces an effective load on the structure, which is R, the external load. And we have some displacement, velocity, and acceleration, which are relative to the ground. And at any point in time, you have dynamic equilibrium. And over a time step, you have an incremental dynamic equilibrium. And you try to solve this equation, basically, without going into details. The problem you have is this is one equation and three unknowns. You've got basically the acceleration increment, velocity increment, and displacement increment are unknown, but it's only one equation, so it's basically 3 times more unknowns and equations. So you can't solve them. What you have to do is make some assumptions. And this is what's known as the constant average acceleration method, and it makes some assumptions which reduce from 3 unknowns per equation down to 1, and then you can solve the equation. It does it with some assumptions. One way of looking at it is that the acceleration is constant over the time step. This is where constant average acceleration comes from. If the acceleration is constant, the velocity must be linear. And if the velocity is linear, the displacement must be quadratic. We don't know what the load is, but probably the best assumption is it's linear. So this thing satisfies all the kinematics requirements, but if you look at, we'll satisfy equilibrium here and satisfy equilibrium here, but if you look at what's happening at the middle of the step, equilibrium is not satisfied in the middle of the step because of this one here. So this satisfies kinematics, violates equilibrium. There's another way in which you can look at that, which is this other one, which says, let's assume everything varies linearly. Then at the mid-step, you do indeed satisfy equilibrium, but now the integral of this is not this, and the integral of that is not that, so you're violating kinematics. But what the heck, it's approximate anyway. And they both give exactly the same equation. It's a very simple equation. The CAA method is one of the simplest methods and is really, I think, the most effective method. There's dozens of other methods. This one is the one which seems to work the best. Those are the equations. You can look at them later if you want to. Perform uses the CAA method. It uses a constant time step. It's the same for all steps. There are some methods available where you have a varying time step, and the old Drain 3D program had that. It doesn't appear to be necessary. The constant time step is fine. In each step, you know the load increment, and it uses load control. We discussed previously using displacement control for pushover analysis. It's better for pushover analysis than load control. You can't use displacement control in dynamic analysis. You have to use basically load. You can't use displacement control. You must use load control. And then within each step, it uses the event-to-event strategy. So it's event-to-event strategy with load control for dynamic analysis. It's event-to-event strategy with displacement control for pushover. Choice of the time step. The time step must be short enough to do 2 things. It must capture the response of the structure, and it must capture the earthquake ground motion. And I'm not going to go into this. My voice is getting tired, and you're getting tired, and I think you can take a look at this. But this is some indications of what you might do to choose the time step. And it shouldn't be too long, and if the ground motion is discretized at, say, 0.02 seconds, you shouldn't use longer than that. And if you use shorter than that, you probably should use a whole divisor of 0.02 seconds, because otherwise some strange things can happen. This is just a segment of a ground accelerogram, just for a few 0.02 seconds intervals. It's an actual record. So if you were to choose a time step of 0.02 seconds analysis, you would be using these points. But if you used 0.04 seconds, you'd be using this point, and 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 this point. You'd be missing some peaks. So you wouldn't be representing the ground motion very well. And if you were to, say, use 0.015, you know, I don't know, here and here, you might start missing some peaks as well. So be careful. You have to do two things. You have to use a small enough time step to capture the response of the structure reasonably accurately, and you have to use an appropriate time step to capture the ground motion. What happens with high-frequency vibrations? What this indicates here, suppose this is some mode shape which has got a very short period, and it might be vibrating in this short period, which may be shorter than the time step. The method still works. It'll still calculate a result, but what it'll do is it'll just calculate an oscillating set of results like this. And usually with a controlled amplitude, the amplitude is often not too different than the proper one, but clearly, you know, this is not a very good approximation to this. So if the time step is long compared with the period of vibration of the structure, you're not going to get an accurate result. And in any particular mode, to get a reasonably accurate result, you need a time step of no more than 1/10 of the modal period. But in any structure, you've got all sorts of high-frequency vibrations floating around, and many of them are going to be, most of them are going to be, in effect, have periods which are shorter than the time step. But the CAA method works fairly well, but on the other hand, it's not a good idea to have these things floating around. And this is one of the reasons why I strongly recommend that even if you use modal damping, you put in a small amount of beta K damping. And then for these very high frequency components, even if it's a small amount of beta K damping, it'll get rid of these things, and they'll be so small they won't create a problem, and it won't really alter the response very much. So let's conclude this session. There's some things that it's important to keep in mind. Structural analysis is not an end in itself. It's a tool for use in design. And I hate to say this to those of us who are structural analysts, but all we do is performing a support function to people who are doing design. There will always be uncertainties in the properties of structure, the loads, et cetera, et cetera, et cetera. And there's so many uncertainties. Always will be. You're never going to get rid of them. So the goal is not to get an exact simulation of behavior. That is literally impossible. The goal is to calculate demand capacity ratios that are accurate enough for decision making. That's the reason we use linear analysis, not because it's exact, but because it gives us demand capacity ratios that are accurate enough for strength-based design. The reason why we'd use nonlinear analysis is because it can give us demand capacity ratios that are accurate enough for deformation-based design, and linear analysis generally cannot do that. So that's the goal, and you know, keep it in mind. It's very easy to think, boy, I produced this really complicated nonlinear model. It must be accurate. It's so big and elaborate. It must be accurate. It's not. You have to really, you know, take a look at this thing. Does it do what you want it to do to enable you to make the decisions you have to make? That's the important thing. Okay, we have 5 minutes before we have to leave the house. Any questions?
I guess my question is, how do you get the modal analysis output from Perform?
So why do you need it?
The mode shapes to calculate the force pattern. I know Perform will do it for you in doing a pushover analysis. Right. But if you're doing a modal pushover analysis, you need, for each mode that you're doing the pushover for, you need the torsional moment as well as forces in both X and Y directions, which would need, you need the mode. Oh, so you want to apply the modal forces but give them some eccentricity, huh? Yeah, essentially, for the modal pushover procedure. Is there an easy way to get the displacements at the center of mass of each floor from the modal analysis? Yeah, and except I'm not sure I can tell you immediately. Why don't you send me an email, Graham at csiberkeley.com, and I'll let you know on that. Yeah, good question. Okay, and then another question regarding modal pushover analysis. In your earlier session, you talked about doing combinations. You can combine different pushover analysis to get results. Can you do that with, for the modal pushover, you need to combine all the hinge rotations using either SRSS or CQC. Can you use the technique you were talking about earlier to do that for hinge rotations?
There's a question there, can you do the modal pushover where you do the, where you
do several pushover analyses for one.
We're actually working on it. I think so, and I'm not certain because there's no CQC option in Perform, but there is an SRSS option available in the envelopes combination task. And I'm actually currently working on it with Professor Gold and Professor Chopra to see if there's anything else we need to add. So right now we're working on it. I'm not certain yet whether you can do it or not.
Thank you.
Well, those of you that stayed for the entire session, thank you very much. You showed tremendous fortitude. So did I.